Okay, let's talk about mixture problems. So mixture problems, right? So mixture of two solutions specifically. So the goal in this section, well, you've been solving linear first order differential equations using the integrating factor, but we haven't done an application. So the first application is going to be we want to model obviously a mixture problem using a first order differential equation. Okay, so that's the goal. That's what we want to do. Okay, so we want to solve the differential equation, but what is a differential equation that models these mixture problems? So let me go ahead and write it. It's going to be a general differential equation, and of course depending on the values of the problem. So dx dt is going to be equal to capital R sub I minus R sub O, not 0. And I is for input and O is for output. And let's go ahead and just write this in words. Okay, so let's make this a little bit smaller here. Okay, so let's define these guys. So this is our differential equation, and right, x of t, right, is the solution that you want to find, and x of t is going to represent the rate, okay, important, the rate at which x of t is changing in the tank. And I'll draw the tank a little bit later. I mean, it's right there, but with some color with the inflow and outflow rates. So that's what x of t is. And then we also have r sub I, which is, again, the rate at which x of t is entering the tank. And of course our sub O is, well actually this guy, we call that the inflow rate, right? So the rate at which x of t is entering the tank is called the inflow rate. And then of course our O, we can say, let's see, the rate at which x of t is so leaving, let's just write it, the tank, right? That's called the outflow rate. And let me go ahead and write it. And okay, so we have our inflow rate and we have our outflow rate. And well, since I have the picture here already, here is my, so inflow rate, right, and outflow rate. So liquid is being pumped in, so R sub I, and this is going to be my R sub O, right, and we can, fill it up with water, for example. So this is the big picture, right? The big idea. This is the main differential equation that you want to use when you're mixing two solutions. The goal really now is just to, we have the differential equation and we can solve for x of t, but we need to determine what R sub I is and R sub O is. What are the expressions? And the book, this is actually, if you want to refer to the book, this is equation 16 in your book on page 52. And basically the Ri that they're talking about, let's see, let's put it in blue. Your capital Ri is little ri ci, that's a product. And then we have Ro, or R sub O, and C sub O. And if you're looking at the book, it's actually fine here. You can I mean, you can just read off of it, but basically, RI and your RIs and CIs or COs are definitely constants, and they your C naught actually denotes the variable concentration. And let me actually just write that in. So I'm here talking about these guys, and your C naught or CO. If I say C naught, I really mean C sub O. It just looks like a 0, obviously, so I'm used to C naught. That's always going to be X of T over V of T, right? So the variable concentration of solute in the tank at time T. So that's what you need to know in order to do this problem. And notice I introduced, right, the V of T, which is the volume of the tank, and hopefully that's obvious, the fact that you're pumping, water in and straining out. I mean, you're talking about volume. You're obviously filling the space. And your RI, your capital RI, is actually, it's always going to be greater than your R naught in our case. And again, I think that's about it. And I will do a concrete example right after this video.